Hi Tejaswini. Hi Jay. Can you hear me?
Hi.
Yeah, hi.
Do you want to wait another minute or so
Yeah, we
to
would wait.
see?
Yeah, we would wait. Yes, yes. Tejaswini, would you know if Kamal would be able to join? There was one thing we want to discuss.
See, he hasn't been joining, so I don't think he'll be able
It's
to
okay.
join.
Okay. I think that part we can discuss offline again. Yeah, okay.
Tejaswini, his email is bouncing. He's still with Microsoft?
He is not actually, but
Okay,
he is
that's
contributing independently. So yeah, I think I don't have a way of communicating, right?
nice.
Other than GitHub is probably the best way to reach him.
Got it.
Oh, then maybe I reached out to this Microsoft email. Maybe I should. Yeah.
Yeah, I mean, I guess you could try the email he uses for GitHub. That's one way.
Okay. Yeah. Let me do that.
But I mean, if this is so, which part exactly did you need help from him?
For the cleaner modeling, we need to change the size of an existing structure. And Kamal said it's possible to do the serialization, some changes in the size, serialization, deserialization, something he said can be done. But he said it's a good topic to discuss in the SAI community. I had assumed he would join, so I sent an email to his Microsoft email ID.
Okay. Yeah,
Let
I
me,
think you can try reaching out, but if you don't hear back, then like maybe we can discuss. I'll see who else can
okay,
like
thank
I'll
you.
see how this can be done.
Yeah, okay, yeah,
Okay, I think we can probably get started, right?
yes, yeah, okay. Uh, Today we want to cover the credit-based flow control as defined in the UC 1.2 spec. And before I start on the discussion, I just wanted to remind, if you belong to an organization that has not signed up with the UEC Ultra Ethernet Consortium, we'll have to follow the instructions Jay had explained earlier in this pull request. So we need to sign an agreement form for non-UEC members, so that I can incorporate the feedback that we get from non-UEC members. Just a process that's been defined earlier. Uh, that said, we can go to this feature. So what is credit-based flow control? This feature is used, it's a link layer mechanism used to support lossless frame delivery. So it avoids packet drops due to buffer overflows in the receiver. So the main idea is uh, a sender would send the packet towards the receiver only after ensuring that the receiver has enough buffers before it sends the packet. Okay, the protocol is in detail defined in the UC 1.0 spec, chapter section 5.2. Here we'll just try to have a brief overview of what the spec is, so that we can understand the SAI attributes and objects. So the goal of CBFC is to make sure the sender sends a packet out to the receiver only after ensuring that the receiver has enough buffer for this packet. To do that, what happens is the receiver tells the sender how much is the buffer available for that uh, port, and then the receiver sender then manages the uh, buffer space on behalf of the receiver. We'll look in detail how that's done in the next section. Before that, two things to notice. CBFC, every port has both a sender and a receiver function, and both of them uh, are negotiated and configured independently. For example, the CBFC sender on the left-hand side and the CBFC receiver function on the right-hand side are done together. And the configuration of the CBFC receiver on the left and the sender on the right can be done independently at a different time. So that's so what we'll be looking at is, for the sake of this discussion, we'll look at uh, one sender and one receiver. The same thing will symmetrically work for the other direction. The next new concept that's been introduced in CBFC is the concept of a virtual channel. A virtual channel is a logical separation of a set of packets that come on a port. And this logical separation is done so that all these packets have their own independent buffers or credits used. And what this allows us, right? It allows us to ensure that packets of one virtual circuit do not block or interrupt the behavior of another virtual channel. So within a port, we can segregate traffic based on the traffic class into different virtual channels and ensure that packets of one virtual channel do not do a blocking or impact the other virtual channel. So that's the concept of virtual channel. And CBFC spec supports up to 32 VCs per port, and each device could support any number from 1 to 32. So this is the thing. Then this, for us to understand how the protocol works, how the mechanism works, briefly, these are the state variables that are maintained. The state at the sender function, what are the state maintained is the total credit available on that port. So this is what the receiver tells. The total amount of buffers at the receiver is told to the sender. That's called this total credit limit at a port level. These are all, these two variables are at a per port level on the sender. So one is the total credits available at the receiver, and the other is of the total credits available, how much is already been used. So these two are at the port level maintained at the sender. And then On a per VC level at the sender, we maintain number of credits consumed and number of credits freed. These are what they call as cyclic counters. The idea behind these counters are they keep on increasing till they hit the 20-bit value and they wrap around. And what would happen is always the credits consumed will be higher than the credits freed. So by doing a delta between this at any point in time, we can compute what is the actual credits being in use currently. So this is credits consumed and credits freed. That's maintained at a per virtual channel level. And then there's a credit limit. So in case the receiver says that the buffer is partitioned per VC, then what is the buffer size for a given VC that is told by the receiver to the sender, and that is maintained as a sender credit limit per VC. Similarly, the sender also maintains per VC level how much is the credits currently in use, and it makes sure at any point in time the credits in use is always less than equal to the credit limit for the VC. So these are the variables that are maintained at the sender. Similarly, at the receiver, uh, per VC, the receiver maintains the number of credits being consumed at the receiver per VC and number of credits that have been freed at the receiver per VC. These two are again the same cyclic counters, and always the credits consumed will be a number larger than the credits freed.
So sorry, Ravi, sorry, I joined a little late. Can you give me a little bit background on what is VC here, like per
Sorry,
port?
So the idea is today, if let's say there's CBFC, the sender and receiver are operating in CBFC mechanism, okay, the what we can do is what the spec says is you can segregate the traffic between the sender and receiver into different virtual channels, and based on the traffic class, you can segregate them into different virtual channels, and traffic on one virtual channel would not affect the another virtual channel. So it allows a kind of isolation between the different virtual channels on the same port.
Yeah.
So
So Ravi, just to
this is a
clarify,
software-based or hardware-based mechanism.
It's hard to
Vineet, I was
say you.
clarifying that. So VC is nothing but a priority class in a traditional sense, what we use, right? DSCP is or a TC, like in SAI we refer. It's nothing but a TC, but in the CBFC world, they call it as a VC, virtual channel.
So this is more like a PFC kind of mechanism, or
No. It's basically a traffic class. It's like a DSCP code point that this traffic class will get this kind of a priority behavior, just like what we have today.
so
TCQ.
so today what we usually do is, right, we usually map any DSCP to any one of the 8 TCs, right, and then we use PFC to flow control individual.
Yeah, how flow
Right.
control is happening, that's separate, but the remaining part is identical.
So, but here looks like we have 64 VCs per port, right?
32 VCs per port.
32, sorry.
Yeah.
So there are 32 traffic classes or priority classes
Okay.
within a port. Yeah, and that's different from your DSCP code points.
So how will this work along with like DSCP/PFC mechanism we have today? How will they coexist or not?
So just to say, right, so traditionally there are two ways to do. CBFC is a mechanism to achieve the same thing as what PFC does. Okay, but the spec allows. Let's come to this complex case of CBFC and PFC coexisting. But the simple idea is CBFC is an alternate for PFC in the normal sense. For example, what happens is the PFC, the receiver does all the headroom calculation, all the buffer calculation. And when the buffer is going to go out of, it's hitting a buffer threshold, the receiver sends a pause frame.
Correct.
Here, instead of that, what the receiver does is receiver tells a per VC or per code point how much is the buffer. The receiver sent the entire information to the sender, and sender makes sure before sending a frame, it checks whether buffers are within limit and sends it out. Okay.
But
So this is like an
but then if this receiver and sender are not from the same vendor, let's say, so how will they, I mean, do this buffer? Because usually they have their own buffer
Yeah,
space and
I
they
think
do
there
it,
is a
right?
notion. I think that will cover, maybe if you give some more time, right? We'll talk about what's the credit size. There is some kind of normalization that's being done.
Okay.
We come up with a unit of tokens called credits. Okay. We carve the buffer cells into credits and then try to normalize across vendors.
So, so,
Maybe
so,
that
so,
will, yeah.
so one thing, what is the benefit of this over PFC? But I mean, why do we need this? I mean,
Yeah. So one is this can go scale more than number of classes that what PFC can support.
mhm,
PFC limits at 8 and this can scale more. Okay.
mhm,
And then there are other benefits, right? For example, if we what happens is, for example, if we do some dynamic load balancing, other aspects, right? They the center knows exactly on each link how much is the current ports already in use, buffer in use, or all this at the receiver. So some kind of things. So there are multiple ways to use both the PFC and CBFC, but common differences, right? CBFC uh, supports more number of lossless channels.
so are you saying we will use either or? Is that what it is?
But the real complex cases, the spec says both CBFC and PFC can exist for simple reason, right? What will happen is CBFC took care of sharing a given port or given VC buffer is maintained by the sender. Okay. Let's say the receiver, I know this receiver has a specific X amount of buffer, and this X is or per VC or something, I've separated something. And this sharing, I can always send it to the sender, and sender knows how to manage all this buffer. So that can be done. So in this case, we don't need PFC. But let's say there are some other resources that shared across different entities in this. It's not per port, but let's say something shared here, right? For example, let's say all the ports in a given pick or a port group, right, have some extra resources to be shared, right? So to protect that, they still might use PFC. Okay. So what
Really,
is, yeah.
yeah, so in a most simplistic terms, you can think it as CBFC is a sender-based control, and where sender will send only how much it is negotiated between the receiver and sender. And PFC is a receiver-based control where if receiver does not have enough buffers to accept the traffic, it will assert PFC control. And as Ravi was saying, that although it's not very beneficial to have both, but the spec does not mandate that it's mutually exclusive, and they can work together if needed.
Okay. So it looks like if the CBFC is working fine, then PFC may never trigger, right? That could always happen.
Exactly. If you have tuned the network correctly using CBFC, then PFC should never get asserted.
Mhm. Okay.
Is my understanding correct, Ravi?
Yes, Jay. Depends, yeah. If we can partition the shared resources, right, across the ports or something, yes, it should not happen.
No, but I mean, if CBFC is working like a negotiated, like it's like more like a QS policy, right? We are negotiated between the two ends, and then if it's not going to send more than what is negotiated, then PFC may not come into picture. PFC
Exactly.
will come
Yes.
into picture when there is you're trying to use more resources than you should, right?
Yeah. Yes. Yeah. I think that's what they're saying is this. The use case they're saying is there could be some other resources. What we are just thinking is in terms of the port buffer, right? There could be some other resources or some other things that could get congested at the receiver, which just based on just a number of credits, right? We would not know those kind of resources that go under contention. Today with PFC, right, whether it's a buffer getting flown or any other something happening at receiver, the receiver can internally find some mechanism to find that and then do a center flow control. But CBFC is taking care of only the buffer congestion aspect.
From center point.
A quick thing. Is it not useful when you have CBFC supported port on one side and non-CBFC supported port on the other side? Maybe an older switch.
Yeah. Then we'll only
Then in that
fall
case,
back to PFC.
we'll fall back to PFC. That's what I'm
Yeah.
saying. That's
Yeah.
one of the use cases for having PFC on the CBFC controllable switch.
Yeah. I think the question is having CBFC and PFC both enable together. The spec allows it, but I think we should leave
Oh,
it.
I see.
Yeah,
Enabled
yeah,
together.
spec,
Okay.
yeah. But I think
Alright.
when this we'll leave it to the UC spec, right? I think these details are in the UC spec. We'll leave it. Yeah.
Okay.
Yeah. Okay. So let's me go back.
Sorry, one more question. So this can
Yeah.
be enabled on the existing switches today, or this needs some support from hardware?
It needs all is a hardware-based
Oh,
mechanisms.
okay, okay.
Yeah, yeah. Even VC, right? How to check the available credits per VC, etc. All this needs hardware support.
Okay, thank you.
Yeah. So we just talked about state maintained at the sender and the receiver. So there's some per port level state and some
One
per VC
question
level
is
state.
in the software, how we identify the VC? Like we keep some.
Yeah, we'll come to that. How do from the packet? How do you identify which VC a given packet belongs to? There are some cost maps. We'll come to that next. Okay. Yeah. Then okay, we just look at the state, and then the next level is there are some message flows that happen. Special messages will be sent between the sender and receiver to make sure the credits consumed and freed at the receiver are known to the sender. So two message types of messages are there. One is called the credits freed update messages. So whenever messages are freed whenever the buffer is freed at the receiver, let's say the packet that was stored in the buffer gets drained or transferred out, then the receiver uses this CF update messages to let the sender know that a replenish the credits at the sender. So that is the CF update message. And these don't use traditional Ethernet packets. Instead, I use special control ordered sets. So this is one type of message. The other type of message is credits consumed uh, messages. These are 64-byte Ethernet, regular Ethernet packets, and these are sent from the sender to receiver to make sure, in case, let's say, some packets get lost and buffers don't get leaked. In those cases, periodically, the sender sends credits consumed messages so that the lost buffers are recovered. Okay. I will try to attempt giving a brief overview. The spec is the right source, but let me give a high-level overview of how this works. Okay, so the starting is, let's say the goal of CBFC is the sender ensures before transmitting a packet, the receiver has enough buffer space before it sends a packet. How it's done is, let's say this is the receiver. The receiver has n number of buffers per VC. So this information is told to the sender during the initialization of CBFC. The sender knows per VC how much is the buffer size available. Okay, and this is normalized in terms of credits. So what is credits here? For example, typically all the packet buffer is in terms of cells which are dependent on different hardware. So what happens is what is the native cell size? What is the cell size of the receiver is told to the sender, and sender goes and checks what are the different cell sizes it can support, and the sender picks the nearest cell size which is greater than or equal to the receiver cell size. Nearest cell size, the sender picks the nearest cell size which is lesser than or equal to the receiver's cell size. Okay, and that is what is called the size of a credit. And once the size of credit, this buffer is partitioned into a size of credits of size which are both understandable by both sender and receiver, irrespective of the cell sizes each platform uses. Now, once we are talking in terms of this normalized credits, okay, the receiver will now will tell for each VC how much credits is available to the sender. So this is what is called the number of credits per VC. This is the credit limit per VC. This is now known to the sender. Now, whenever the sender sends a packet, it first checks that whether the credits in use at the sender, or if you add the current packet credits for this packet, how much of credits the packet would consume, how much of credits the packet would consume. If that is added to the credits already in use, it should not exceed the credit limit told by the receiver. If this is assured, then the sender would send the packet to the receiver, and it will update how much is the credits consumed and how much is the credits in use. Both rules are updated the sender. Now, when the receiver gets this packet, first it will store it in the buffer and it will increment the credits currently used for that VC. Later, after some time, let's say this packet is getting forwarded out on some other port. When this packet gets forwarded out in some other port, the receiver then increments the credits feed. So this packet is no longer in the VC's buffer. So the VC's credits feed counter will increment. And then periodically, okay, there are some rules, some timers specified so that we don't send too many messages, credit feed messages in the network. There are some rules set, like as at least the minimum number of bytes that should be transmitted before you send out another credits between two credits feed message. So once you send out if the timer is matched, okay, then the receiver sends out a message to the sender saying that, hey, this is the current credit feed for this VC. What would be the reality would be the credits feed, the sender would be always lesser than the credits feed at the VC. So that difference tells the number of credits that have been freed up in this interval at the receiver. So the credits in use will be reduced by this difference. And then the credits freed will also be will then be updated to the new value. Okay, so this is a high-level way of the way the spec works. So basically, these messages are sent periodically to make sure the credits in use are computed not by sending the credits in use exactly, but just keeping a running counter of how much credits was consumed and how much of them are freed. That running counter is always being sent. And by computing delta between the credits consumed and credits freed, the sender can always compute what is the current credits in use at the receiver. So this is the main idea of it. And then there are some more things like a max spacing timer to ensure that in case this credit freeze message gets lost, how to make sure periodically that lost message is replayed and it's recovered. That's one way of it. And then another kind of credits loss that could happen is, let's say, when this packet is sent out, the credits in use has been incremented to the sender. But let's say this packet never reaches a receiver. So then the receiver will never free these packets, and this might be a leaked credit. To avoid that, periodically, what happens is the sender tells, hey, this is the amount of credits I have consumed. And if this number is higher than what the receiver is having, I've stored it, and that delta is a lost credit, and that will be periodically sent back to the sender. Okay. Yeah, I think this is a little intense, but this is a high-level overview of how the protocol works, and the spec could have a detailed explanation how this all works with some lot of ladder diagrams. Yeah. Yeah.
Very good question. So on the receiver side, right? Let's say the congestion scenario. So in that case, you're saying that the credits will not be freed and it will slow. The sender will not send more packets until he gets the free credit back. Is that what you're saying?
Sorry, give 1 second. I'll just say one. Sorry.
So what I'm saying is on the receiver side, let's say there is a congestion. Let's say in the beginning there is a good case where everything is flowing good. We have credits freed and then sender keep on sending, right? But let's say there is a congestion happening on the receiver side for some reason. So in that case, the credits on the receiver side, it will not mark it as a free, right? So, and that will be communicated to the sender and sender will not send more packets. Is that how it is going to work?
Maybe no. Maybe I didn't fully understand the question, but maybe let me repeat, right? So that what happens. So what you're saying is, let's say up to 2B, it's all fine, right? 2B, you send out some data packet here, and you also updated how much the credits used. And then what you're saying is this, for let's say there's some head of line blocking the egress port, and this packet is never getting drained. Is that the question?
Yeah.
Okay.
Yeah.
In that case, nothing needs to be done. But then what happens is, right? You can keep on sending some more packets as long as this buffer gets filled up. Okay. Initially, the credit limit will be equal to the number of credits per VC, right? So you can keep sending all these packets, and once that limit is set, okay, what would be happening is this check will never pass. The credits in use and the credits in credit limit will both be equal. So the sender would not be able to send further packets. Okay. So once this drain happens, you'll have to wait for this freed message so that the credits in use will be reduced.
Okay. Okay. Thanks.
Okay, yeah. There are some ways we have described something in detail here. Yeah. Okay. So now, yeah, I'll go through this. Okay. So now I think this is just the overview of the protocol. It's the conceptually, it's very simple. All we are saying is this receiver tells how much is the buffer. Either it can tell at the full port level how much is the credits across all the VCs, or the receiver can choose to sell per VC. These are the credits. Okay, and then the sender manages on behalf of the receiver. So that's the idea. So now let's see how we have modeled it in the SAI. Okay. So the major changes happen in this port object and a new object called a VC object. These are the two major changes that are happening. In the port object, uh, first we have a bunch of attributes to decide to do the credit normalization, to understand how much is the credit size at how much is the credit size or the cell size at the receiver, and what are the different cell sizes that the center can support, and find nearest value which where the cell size of the sender is less than or equal to the that of the uh, receiver. Okay. So one set for those. Similarly, at the receiver, for storing each packet, there could be some overhead, some metadata, or something would be stored, right? That overhead, what is the overhead at the receiver? All this, there are ways for it to be understood from the receiver and then get programmed to the sender. So a bunch of such attributes are there. And then this another set of attributes are for the different cost maps, how to derive the TC, regular TC, all these cost maps. And something new is how to derive from the TC, how to derive VC Prakash question, right? For all those, there are some port objects which to which we bind some cost maps. Okay, so we'll come to those. So the new cost maps are there, and that cost maps will be attached to the port. And lastly, the port itself has some limits per how much is the credit limit, etc. So those information is stored in the port. And lastly, there are a lot of stats related to the CBFC operation. So this is changes in the port object. And then uh, some new cost map types have been introduced to derive the TC. And today only .1p is supported in OCP-SAI. We are extending it to have .1p plus DA to be derived with TC. The spec says all the 4 bits can be used to derive the TC. And some attributes in the queue to enable or disable DQ. This is needed when you want to convert a VC from lossless to best effort or best effort to lossless, right? For that process, we need to use simply stop the drain DQ, since simply stop NQ. For that, we need some new attributes. And then a new thing is the virtual channel object. So this virtual channel object controls the credits associated with a given VC. All the credits, how much is the credits used for a given VC, and whether the VC is lossless or best effort, all these are being controlled by this virtual channel object. And uh, how to specify the credits? One way could be the credits could be, you could have unique credits per VC, it's completely isolated. The other case could be the spec allows a variety of credit management. Other case could be some parts would be reserved and some parts of the credits are reserved per VC. And then there will be a shared credit pool, which can be shared either statically or dynamic thresholding can be done to share the remaining credits across the VCs. So to do all this, we have modeled something called the credit profile and credit pool, which behave exactly like what our current SAI buffer profile and buffer pool operate as. So these are the major objects that we have introduced for the CBFC operation. Any questions so far?
Very quick question. So for the credit, what is the unit? Is it a cell or is it a byte?
The credit is in terms of bytes.
Okay.
Okay, and this bytes is actually coming from the receiver cell size.
Okay.
So that's a good question. So we need an implementation typically may be operating in a cell boundary, and it has to convert the cells into byte for CBFC credit exchange.
Yeah, because every architecture has a different cell sizes, right? So
Right.
on one side the credit means something else and the other credit means something else, right? So that's why I
Yeah,
wanted to
yeah.
know how
So
do we
the Right.
Yeah.
So in this case, the boundary condition will get triggered in that, let's say there is approximation of a cell which is done in a byte, right? And the credit allocation happens in byte, but the implementation will operate still internally at a cell boundary, right?
Mhm.
So those are the boundary conditions, but they are all implementation details. SAI
Yeah.
just
Yeah.
abstracts everything out.
Mm.
Yeah.
Yeah.
Okay.
Yeah, I think, yeah, if time permits, we'll let go through that section where we say, right, how you discover the cell size at each end and how do you choose, right, the nearest approximated value. I think they're
Also,
in the
these
workflow.
CBFC frames are more like a PFC frames. I mean, I mean, how do we have the format of that?
The format, the way it is, right, it's kind of, yeah, they had a special, one is control data set. It's not even a regular Ethernet packet. It's a control data set. The spec has the actual format. Control
Mhm.
data sets are special link level signaling packets exchange, special link level 8-byte information is being sent, right? So that is the
Mhm.
CF update. So that is where we see how much the credits freed. And then once at the lesser frequency, we'll periodically send the credits consumed, right? So this will be in one Ethernet packet. This is a regular Ethernet packet, 64-byte Ethernet packet. And in one packet, you can cover, let's say, I think up to 16 credit SEC, the credits freed for credits consumed per 16 VCs. So that's the format it will contain, right? So they'll send two messages, two packets or something. I think the spec has the actual details of all how it works. Okay. For side, the internals doesn't matter. So just I didn't go
Sure,
into that
sure.
details.
Yeah,
Yeah.
yeah. Thanks.
Yeah. Okay. So now we just talked about the different objects in place. Okay. So now let's a quick overview, a very high level overview. What happens at the sender?
There are
Yeah.
two
Yeah.
things here in this diagram. One is says this yes TC to VC, and other is Q to VC.
Yes.
And then dot one to VC. I think dot one to
Yeah, I'm
TC
just
you
going to cover
explained.
that all this. I'll just cover here. I think all
Okay.
this what you're
Okay.
asking, right?
Sure.
This is there in the flow, Prakash. Just no, same question, right question, right? I'll quickly try to see, and if it's not covered, we'll again come back, right? So just to see how this happens, right? Now let's look at what's first happening at the sender side. Then let's go to what's happening at the receiver side. At the sender side, okay, uh, the bulk of this CPFC processing happens on the egress of the sender. Okay. Uh, so before that, whatsoever happening in the ingress is what's happening today. A packet comes in, the packet comes in, and based on the packet's QoS fields, we'll derive the TC. The QoS fields could be a DSP, or what is newly we introduced is a dot one P plus DI bit. This is very identical what we do as a dot one P today. It just includes the fourth DI bit as well. CFA or DA bit. Okay, so with this we derive the TC, and from TC we derive the Q. All this is like what is done today, existing, no change in behavior. And similarly, based on the packets for header, the forwarding logic decides what should be the egress port. Okay, all this is done. Now comes the question: what happens is till this part, this is all the regular flow, and we know what's the queue for this packet on which this given packet should go out. Now, let's say CBFC is enabled on this egress port, and what will happen is this packet from this queue, an additional check today, based on the queue scaling discipline, this queue will be drained, will be dequeued. But just before the dequeue, if the queue to VC, CBFC is enabled on this VC, and the queue to there's a queue to VC map, okay, which tells for this queue what is the associated VC. There's a mapping with the queue and VC. And if VC as CBFC enabled, then before the DQ actually happens, an additional check is done to make sure uh, this VC has enough credits for the given packet before the packet gets DQ'd. So,
Ravi, do we have one-to-one mapping between Q and VC, or is it
yeah,
one-to-many?
it's 1-to-1.
Because you mentioned 32 VCs per port, and
Up to 32. Yeah, up to 32. It
and
depends on
the
the
number.
implementation. Yeah.
Okay, and the number of queues usually we have 8, right? I mean, unicast
Yeah.
queues.
See, number of TCs could be 16, number of 8, right? But the spec on the next gen hardware, right? Spec allows up to 32. If you have 8 VCs and 8 queues, if you have 8 queues, right, you will be able to do only 8 VCs like that.
Okay.
Yeah. If you have more than one VC on a given queue, right, then the isolation is lost because, right, if you want to convert one VC to lossless or lossly, then you'll have to stop the queue from draining and things would happen like that.
But then if you can only do 8, then how are we getting benefited from
No,
CBFC?
no, again, 8 is, you're talking about some specific platform, right? The newer platforms will have more than, let's say, right?
Oh, okay.
Let's say it's have more
Okay,
than
okay.
16 queues.
Sure. Okay.
Yeah, yeah. Okay. So this is what. So now, Prakash, just answering your question, right? So on the sender side, okay, there is a map called Q to VC map, which states before I dequeue from the queue, I want to check which VC this queue is belonging to, and look at the VCs whether I'm within the VC's credit in use credit limits.
I see.
So that's where
So
we
Q
use.
Q to VC mapping is maintained based on the hardware. That if hardware is the old hardware, then it's 1 to 1. If the hardware is new, then we can have
No.
Q to
Hardware is
VC.
new or not, right? What you're saying is, if the hardware is new, there'll be enough number of queues. The CBF still is a new feature, right? It's just a new feature. What we're saying is, the discussion is different. It's just saying, right? If in traditional legacy devices, the number of queues would be 8,
Mm-hmm.
then we can only do 8 VCs, and even PFC can do only 8, right? So that was the question we were trying to
It's
look at.
always 1 to 1, then why mapping is needed?
No,
The Q
okay.
VCs are 1 to 1, then there's no need for mapping, right? Q is the VC.
No, but what we're assuming is Q1 is VC1. Is that what you want to hardcode, or is that what your question?
I just
You're
try to
saying
understand, like I don't have one way or other like preference, but I was trying to understand why the mapping is needed. Mapping is needed when there is a difference between Q and VC, but as far as so far I'm understanding from you, new hardware will have the Qs also same as the number of VCs. Then it's always 1 to 1, right?
1 to 1, but QID and VC
As
may
per
not
my
be on a.
understanding, this virtual channel is going to help with this managing all the CBFC related parameters. I think maybe that's why we need this mapping.
Yeah. So your question is, why not add all this into the queue itself? Is that was the question, Prakash? Is that what you're saying? Why create a VC object in the first place? Is that your question?
No, I was understanding the requirement of the mapping. Mapping is required when there's no 1 to 1, right? We need to map Q to VCs or
How
VC
do you
to
say
Q.
1:1, right? Q doesn't today have any such thing. Are you saying that I'll use, let's say, Q hardware index as something to the VC order index?
I'm not saying preference, but I'm trying to understand that can't we do that way, or why we need the mapping?
How's the mapping done today? What is the state of art today?
I didn't follow. What is the state of art in which?
What? How do we do today? What is the baseline? So you're proposing a mapping between cubes and PCs. Is there such a concept today? Do we do mapping?
The whole VC this is completely new, right? What was shown, this pink is
Okay,
all new.
it's all new. Okay, so in that case, my assumption is you need the mapping to, because you may want to associate Q0 to control VC controller, channel 2,
Oh,
right?
I
So
see.
the association could not be 1 to 1. It could be 1 to N, 1 to M, 1 to P, 1 to Q.
That's what I was thinking earlier, but then he said that new hardware will have the same number of Qs as number of VCs. So
No,
that's
Yeah, it
it's
could be
still, I
same
think Prakash
number,
is
but
saying it's not identity mapping. What you're saying is
yeah.
you are assuming it's all identity mapped, right? 1 goes to 1, 2 goes to 2. Okay.
Mm.
That's not identity
But
function necessarily, right?
Eric, there is an advantage of Qs are because Qs are the existing thing because those are the fixed nomenclature, and that's why we want to map to different VCs. Like Q1 always cannot go to VC1.
We don't need to restrict it, right? On platforms, the restriction is there. You could have a Q2VC, it'll always be identity
VC
mapped.
might have a different characteristics, and it might be required to map different Q to different VC numbers. Or maybe because of you said there are some VC which are the common VCs. No, that is only
What is common VC? Sir, I didn't. Yeah.
No, you are saying the shared resources, right?
No,
That there
that is
could.
still that's coming from different place, right? The credit pool and credit profile will take care
Okay,
of the
that's
sharing.
from the credit pool and profile. Okay, so
Yeah. See, the
then
whole
we.
question is, Prakash, we are not saying the VC and Q should be identity mapped.
So we expect that there will be some different characteristics, and the fixed characteristics because of the hardware. VC might have, like VC1 have certain kind of thing, VC2 might have certain kind of thing, and then Q might be different, and there will be a mapping required between Q to VC. Or simple case could be 1-to-1, but there could be a
Yeah,
complex
flexibility
case.
is just there. Yeah.
Means I don't have the
Yeah.
preference. I'm just trying to understand the
Yeah.
architecture.
This doesn't map to
Simplify
any one architecture, right?
better.
This
Like
just
if you just map 1-to-1, then it's easier, right? Software doesn't need to worry about the mapping, and then with the mapping, a lot of complexity will come in. So
No,
if
but
there's a
you lose the flexibility. Let's say the queues are defined in software, and
yeah.
you want to have that flexibility, and this will be extensible architecture for the future. So you could control it today. You can just simple mapping in the software 1-to-1. But if things change in the future, you have the flexibility.
Yeah. So that's what I'm trying to think of. That maybe the VC might have certain characteristics based on the different implementation, and we want to map a different queue to different VCs. Fine, that's okay. Can go ahead.
Yeah. So this is the maps we talked about, and then the what we're showing red is additional. So up to the queue, everything is same, but from the queue, we try to map it to a VC, and the VC has its own what should be the credits available for the given VC. So this is what's happening at the sender side. The receiver side is pretty simple. On the receiver side, all it needs to know is right. All we need to know is make sure our credits freed and credits consumed, right? Those are correctly accounted of. For that, when a given packet comes in, we'll have to use the same cost bits of the packet to derive the TC. This all is the same as like what's happening today. And from the TC, we have a TC to VC map on the receiver side, which will tell, hey, for this packet, on which VC's credits consumed should I increment? That's it. And now with this, both the credits consumed message will be updated. And eventually when this packet is drained, the credits freed of the VC will get updated, and periodically this will be sent back to the sender. So this is what's happening at the receiver side. Okay, so this is the new map called TC to VC map. Okay, so now let's go through the objects what we talked about. The simpler objects are credit pool and credit profile. They operate exactly like what
That's
today
the
I'm talking about.
another reason, because you want to have the TC to VC map as well. That's probably the reason why we need the Q to VC map as well. I think it's making more sense.
Yeah, because here also we are not saying TC and VC are 1:1. Today
Right.
it's same thing, right? Even TC to Q is not 1:1 necessarily inside.
Yep. Yeah.
Okay. Okay. So now, so what? Same thing. All the this is what we saw, the logical view of how the objects are used, and now just the attributes how they
I
model.
just want to add one thing with respect to the previous discussion, the DC to VC map. So far, we have been not talking about advanced topologies like Dragonfly and Megafly, which also make use of those VCs for deadlock control, the network deadlock control. So that's when we need to have that mapping so that during the setup of the switch based on the overall configuration, things could be set up as to how DC and VC will be mapped to each other. Simply put, your TC may need two VCs for deadlock avoidance. I'm not going to go deep into that, and that will be a consideration as we go along with advanced topologies.
Saying the
Arnav, what you're saying
complex
is
mapping might be required. That's what you're saying.
okay.
Yes, complex mapping will be required, and we are keeping that flexible here. And in most cases, it's a one-to-one mapping. Simple.
Okay.
Yep. I'm done.
Okay, no, thanks. I'll maybe I'll sing with you offline. Okay, so saying Okay, for deadlock avoidance, you need something else. Two things, is it? One TC, two. Okay. Okay, yeah. Let me get back. I think we just have last 12 minutes, right? So this is the credit pool and credit profile are identical to exactly how buffer profile and buffer pool happens. Only difference is buffer pool and buffer profile works in terms of bytes. Credit profile and pool work in terms of credits. So that's all. The same thing. What is the reserved credit size, static thresholding, dynamic thresholding, all this apply here. Okay, that's part one of it. And then there's a new object called the virtual channel. The virtual channel belongs to a given port, and on a given port, which index it belongs to, that's the key attributes. When you're creating the virtual channel, you have to provide them. And so this is going to tell if the receiver, how to identify how much is the credit limit per VC, the receiver. So that's a read-only attribute to get what's the credit limit per VC at the receiver. And then there are at the sender, we need to set a credit profile so that we can do the checks to see how much is the total credit limit and whether the sender is within that credit limit, right? Current usage is within the credit limit. For that, we have something called this credit profile, similar to a buffer profile, all identical things. And then lastly, we have a receiver enabled, sender enabled. Okay, so that only when all this is set up, this will be turned on. So that's what is the enable disable functions of the each direction for the VC. And then we also have statistics at the VC. So these are the same stats we saw here. All these are same, right? What's the credits currently used, credits in use, and this is running out of credits consumed. It keeps on incrementing, and then there's a credits freed, and similarly on the receiver side, you have receiver credits consumed and receiver credits freed. So it's all everywhere we see something a sender function and the receiver function both will be on the VC. And then we have the existing cost map. So there's already a cost map structure. We are bringing in new types. One type is the .1p plus DA to TC derivation. And then the other types are TC to VC and Q to VC. So there's a new types defined. And since there's a new field called VC and a new field called .1p DA, we have to exchange the cost map params to add these two new attributes. Yeah, so this, let me, minus.
Very quick question. So
Yeah.
does this mean we can only enable CBFC when the neighboring, like the sender and the receiver are of like similar buffer profiles? I mean, buffer sizes. Like we can't have maybe a device with the deep buffers connected to a shallow buffer device, right? To have
We
CBFC.
can, let me see how to write. Okay. Okay. You're saying finally, okay. Let me,
I'm just trying to understand like where can we use it, where cannot we use this? Yeah, I'm just assuming given it is based on the like how much buffers you
yeah.
can, right? So I was thinking if there is a device with a deep buffering and other device with a shallow buffering, then whether they can make use of this or not. That's what I was thinking.
Yeah, there is
Doesn't,
there is no such assumption in the proposal or in the spec. Any two devices, I mean, by definition, two vendors will have a different buffer profiling, right? So there are two things. One is the LLDP exchange, which is a little bit at a course level. I think, Ravi, do you recall if the number of credit exchanges there in the, it's only,
it's part of the LLDP, Jay, you're right.
it's part of LLDP,
total credits, right? Yeah.
Yeah, total credits. So there is a LLDP exchange, LLDP proposal, which is there. And that what it will do, it will create a least common denominator for the peering links and come up with the credit allocation. And if, let's say, you're not doing a LLDP exchange, then what Ravi's proposal will have an explicit credit count.
Okay. And this exchange is a per VC level or per port level?
Both
This
happens.
is per port level. This is all at a link level. VC is abstraction, is a logical abstraction.
Okay.
Yeah.
Right.
Yeah. So just to say, right, just to say what happens is, right, see, the only thing the credit size that matters in one direction, right, from the sender to receiver. Okay, there's no interaction between this buffer size at the center. All we are worried about is only the ingress buffer size at the receiver, right? That's the only thing that needs to be known.
Okay, got it.
That's part of it. That's
Okay.
okay. And
So
then the
basically,
second question.
even though the devices are of different buffer size, they can advertise different size on the other side, and
Yeah,
then
yeah,
the site can
because
control
that's
that.
yeah,
Okay,
because
okay.
both are negotiated independently, both directions,
Got
right?
it.
Each direction's independent negotiation. And
Got
then
it.
what Jay has talked about it, that's the second more interesting part, right? So this now for given packet, let's say my cell size is 256, and I just sent a 64-byte packet. Okay, but my cell size is 256. So even though for a 64-byte packet, I used one full cell of 256, right? Okay, so to do that, that's exactly what Jay said. So what will happen is, what is this native cell size, native credit size, right? That information we read from the receiver, and then LLDP or some control plane will exchange this information, send it to the sender, and sender will see what is the native credit sizes it can support, and they'll find the least common denominator, where in this case the sender should choose a cell size which is less than or equal to what's the receiver cell size. So the sender doesn't over account, sender doesn't under account, right? So that's what we talked about LLDP. So there are a bunch of read-only attributes to figure out what is a native credit size. Similarly, if a 64-byte packet is sent, there might be some extra metadata that's being put. Okay? So make sure the packet, right? Sometimes the metadata can cost take it use two cells. So all this, right? For all this, there are read-only attributes for it to be discovered and sent to the other side, so that the board understand exactly what is the overhead for in each direction. And finally, there are some create and set attributes where the negotiate value is finally set and exchanged to both sides. All the read-only attributes are asked to figure out what is the native device capability on both sides, and then the negotiated value will be set using the create and set values. Okay, so that's where this is happening. So this where all this, right? For the all the first few parameters are to understand the packet override and all this, both on the sender and receiver functionality is there. So this all, well, that's part of it. Then comes the credit limit. So this is the receiver will send what's its credit limit. Let's say where it's yeah. So this attribute is used to understand what is the total credits on a given port uh, available at the receiver. So this information is sent to the sender, and sender initializes it as the total credits available at that port. So this is the credit limit what you have done. And then there are a bunch of timers associated. Okay, the timers are to ensure that we don't send too many credits consumed. We want to tune based on the network, right? So that is there are timers there. So this timer is in uh, unit of time, and then there are some other condition rules where there's a minimum number of bytes that should be transmitted before two control order CF controller sets are being sent. So those rules, right, and are there, and this max spacing is to ensure that in case there's no messages, last free message was lost, last control CF message was lost, right? Uh, then the credits are leaked. The CF max spacing is to make sure we replay the message once in a long window so that those lost messages are recovered. The rest are all the maps we talked about, the newly introduced maps. We are giving attributes to bind it to a port, all the new attributes. And these are just for bookkeeping, some read-only attributes. So these are the port attributes. And then again, we have some statistics. Uh, uh, Credits used at some sender statistics and some receiver statistics. On the sender, we know how much is the credits used and the watermark of the credits used. And it'll have both the number of credits consumed and credits freed message that we sent out when I am the uh, CF update. CC update is when I am the CC update is when I'm the sender. And for receive functionality, we'll have a CF update messages that we transmitted. Okay, so these are all the statistics at the port level. Lastly, the queue level, we have some knobs to enable DQ and disable enable and disable DQ and queue, right? For that, we have knobs, and these are needed when we want to move from, let's say, lossless VC to a convert it to best effort or best effort to lossless, right? We need to temporarily stop the DQ, stop draining, right? For that, these are there. So I'll quickly rush over the capability queries. This is all regular stuff, capability query. And initializations, we just talked about how to, what Jay suggested, right? We need a way to discover the hardware capabilities and then negotiate some parameters. Okay, so these are the read-only things are the way we read from the different sender and receiver. LLDP will make sure that it goes to both sides, and the control plane and protocol will figure out what's the negotiated values, and those will be finally set. The negotiated values will be set. Okay, negotiated value for packet overhead on both should be set at both sender and receiver. The same value should be set. Similarly, on the sender and receiver, the credit size should be set. And then, if the port credit sender, how much is the total buffer size at the sender, right? That information will have to be set at the sender. So all same thing. And this is we have to create virtual channels on the port. Both sides you have to create virtual channels, and both sides you have to enable CVFC so on the virtual channel. We have to bind cost maps. So this is all initialization step. We have to bind cost maps on the port to derive the TC based on the dot on PDAI and TC to Q existing Q to VC, all these maps, right? All this some example code. How do we do this? And this is the more interesting part. This is all initialization. Everything is done. Both sender and receiver know each other's capability. The cost maps are all set up. Now, if you want to convert a VC, make it CVFC, the first step is we keep it false. CPC initially is set to false. We clear up all the statistics, make everything is 0. And then on the sender, we temporarily stop the DQ of traffic from sender going to the going out. We stop the traffic, and then all the VC stats are freed up, all are emptied, and we attach the credit profile on the sender VC. Senders all attached. Till the time the DQ is stopped on the queue, all the credit profile, everything is set up, and then we go enable it on the VC on the receiver side first. Once the receiver everything is set up, we enable it VC on the sender, and lastly we start the DQ at the sender. So basically we make sure the other side, first we stop the DQ on the sender, make sure everything is set up on both sides, and lastly we again resume DQ at the sender. Okay. This is same thing for lossless VC removal. We stop NQ, make sure no new traffic comes to the sender. All the existing traffic in the sender gets drained. And lastly, then we go into disabling CVFC on the sender first and then the receiver later. And lastly, the queue is enabled. I think we're just on time. I think this was right, but we can have some questions here now, right? Yeah. Yeah, any questions?
Ravi, this looks good to me. I think this we have discussed multiple times. I don't
Yes,
see any major changes to it. I will be approving. I again scan through I had only one question, which is a warm boot question, but that's orthogonal. So I'll be approving this PR.
Thanks a lot, Jay. Thank you. Yeah. We see if Jason is also there, because maybe I think Jay, you and me, we have discussed and worked on it longer. So yeah, we are on the same page. Jason was also temporarily for some time he was also attending, and yeah, Aruna, yeah.
Aruna, would you be? Aruna dropped off. Okay, we will catch Aruna separately.
Yeah.
Okay. All right. Thanks, Ravi.
Thanks a lot, Jay. Yeah, thanks, Tejaswini. Vinit dropped. Thanks, Prakash. Yeah, thank you.
Thanks, guys. Thanks a lot. Bye.
Thanks, Ravi. Yeah, and we can schedule a meeting for the other one if needed. Yeah.
I'll try to reach out to Kamal. Yeah. Do you know Kamal's email? I'll email you this just to get Kamal's email ID and how to reach out, right?
Sure.
Yeah. Thanks a lot. Bye.
Sure. Yeah.